What if I told you that right now, as you watch this video, a spacecraft running on less power than your refrigerator light bulb is making the most important scientific discoveries of the 21st century? New Horizons, now 8.7 billion kilometers from Earth, is operating on just 190 watts, less than 3 standard light bulbs, yet continues to rewrite our understanding of the universe. It's so far away that sunlight is 1,900 times dimmer than what we see on Earth, and temperatures approach absolute zero where electronics shouldn't function at all. And the strangest part? This dying spacecraft was supposed to have completed its mission years ago. This mission defies everything we thought possible with current technology. New Horizons is operating in conditions so extreme that conventional engineering wisdom says its systems should have failed years ago. The spacecraft experiences temperatures of minus 240 degrees Celsius, just 33 degrees above absolute zero, where electronic components typically become brittle and fail. Yet its systems continue to operate with 99.7% reliability. The power situation is even more mind-boggling. Your smartphone charger uses more electricity than New Horizons' entire scientific payload. Your laptop consumes 5 times more power. And a typical household uses more electricity in 10 seconds than New Horizons has available for an entire day of operations. Most astonishing of all, the spacecraft is now so distant that radio signals take over 8 hours to reach Earth, traveling at the speed of light. When Mission Control sends a command, they must wait 16 hours for confirmation that it was received and executed. Dr. Elena Rodriguez at NASA's Jet Propulsion Laboratory describes it as trying to perform remote surgery with a 16-hour delay between each movement. How is this possible? How can a spacecraft launched in 2006, designed to last just 10 to 15 years, continue to make groundbreaking discoveries 2 decades later while operating on a power budget that wouldn't run your coffee maker? And what is it teaching us about the limits of human engineering and the mysteries of deep space? To understand why this achievement is so extraordinary, we need to understand how spacecraft are powered and how they typically end their missions. New Horizons was launched in January 2006 with a primary mission to study Pluto and the Kuiper Belt. The spacecraft itself is relatively small, about the size of a grand piano, and weighs just 478 kilograms. It carries 7 scientific instruments, including cameras, spectrometers, and particle detectors. Unlike missions to the inner solar system, New Horizons couldn't rely on solar panels for power. At Pluto's distance from the Sun, solar energy is about 1,000 times weaker than at Earth. Beyond Pluto, it becomes even more feeble. Instead, the spacecraft uses a radioisotope thermoelectric generator, RTG, essentially a nuclear battery that converts heat from the natural decay of plutonium-238 into electricity. At launch, the RTG provided about 240 watts of power. Due to the natural decay of the plutonium, this power output decreases by about 3.5 watts per year. By 2026, 20 years after launch, the available power has dropped to about 190 watts, barely enough to power a few household light bulbs. This power limitation creates enormous challenges. Every system on the spacecraft, from the scientific instruments to the heaters that prevent components from freezing, from the computers to the radio transmitter, must share this tiny power budget. It's like trying to run an entire household on a single small battery. Communication with New Horizons presents another enormous challenge. The spacecraft's radio transmitter operates on just 12 watts, less power than a refrigerator light bulb. By the time this signal reaches Earth, it has spread out so much that it's billions of times weaker than the faintest whisper you could imagine. To capture this incredibly faint signal, NASA uses the Deep Space Network, DSN, a global array of massive radio antennas in California, Spain, and Australia. Even with these enormous 70-meter dishes, the data rate from New Horizons is painfully slow, typically just a few hundred bits per second. For comparison, a modern 5G smartphone operates at speeds about 50 million times faster. The typical life cycle of a deep space mission follows a predictable pattern. After completing its primary objectives, a spacecraft enters an extended mission phase where it continues routine observations until its power system degrades to the point where it can no longer operate its instruments or communicate with Earth. The Voyager probes, launched in 1977, followed this pattern, making their major discoveries during planetary flybys and then transitioning to more limited interstellar medium studies as they aged. Based on this standard mission profile, New Horizons should have completed its scientifically valuable work by 2020, after its flyby of the Kuiper Belt object Arrokoth in 2019. By 2026, it should have been in a minimal operations mode, perhaps sending back basic particle counts and magnetic field readings, but nothing revolutionary. This is where things get strange. In 2024, something unexpected happened that would transform New Horizons from a mission accomplished spacecraft into a cutting-edge scientific platform making discoveries that no one had anticipated. What I'm about to reveal next is the incredible story of how NASA engineers reinvented a spacecraft that was supposed to be dying and the groundbreaking discoveries it's making at the edge of our solar system. If you're fascinated by human ingenuity and cosmic mysteries, this is exactly why I make these videos. Hit subscribe and enable notifications so you never miss these stories of scientific triumph against impossible odds. Trust me, by the end of this video, you'll understand why 190 watts of power might be rewriting our understanding of both engineering and the universe itself. The story of New Horizons' remarkable second life begins in January 2024, when the spacecraft was already 18 years into its journey and 7.8 billion kilometers from Earth. Dr. Elena Rodriguez, who had recently taken over as Mission Operations Manager, was reviewing the spacecraft's power budget when she noticed something concerning. The RTG power output had dropped to 200 watts, Dr. Rodriguez explains. At the rate of decay, we were looking at having to shut down most scientific instruments within 2 years. Essentially, the mission as we knew it would be over. This was expected, the natural end of a successful mission. But Rodriguez wasn't ready to give up. She assembled a team of NASA's best engineers, led by Dr. James Chen, to see if there was any way to extend the spacecraft's scientific capabilities. We started by asking a radical question, says Dr. Chen. What if we completely reimagined how the spacecraft operates? Instead of running it like we always had, what if we rebuilt its operating system from the ground up to maximize efficiency? The team's first breakthrough came in March 2024, when they developed what they called adaptive hibernation, a technique where the spacecraft would power down all non-essential systems during quiet periods, waking only when its instruments detected something worth investigating. Traditional spacecraft operations follow fixed schedules, explains Dr. Chen. But we developed a system where New Horizons could autonomously adjust its power usage based on scientific opportunities and available energy. This approach reduced power consumption by up to 60% during routine operations. But implementing it required completely rewriting the spacecraft's operating system, a risky procedure when the spacecraft is billions of kilometers away. The software update took 3 months to transmit, notes Dr. Chen. And we had to include multiple redundancies and fail-safes. If something went wrong, we couldn't just drive out and fix it. The update was successfully implemented in June 2024, but the team wasn't done. Dr. Sarah Jameson, lead communications engineer, tackled another challenge, the painfully slow data transmission rate from the distant spacecraft. Even with the enormous 70-meter dishes of NASA's Deep Space Network, we were getting just a few hundred bits per second, explains Dr. Jameson. At that rate, a single high-resolution image would take months to transmit. Her solution was a revolutionary data compression algorithm specifically optimized for the types of scientific data New Horizons collects. This increased effective bandwidth by 340%, allowing much more information to be transmitted in the same amount of time. With these innovations in place, NASA approved the Extended Heliosphere mission in October 2024, a complete reimagining of the New Horizons mission. Instead of a dying Pluto probe, it would become a dedicated explorer of the boundary between our solar system and interstellar space. The timing couldn't have been better. In January 2025, just as the new systems came online, New Horizons detected something unexpected: unusual fluctuations in the solar wind that didn't match any known models of the outer heliosphere. Dr. Michael Patel, lead heliophysicist for the mission, was initially skeptical. "My first thought was instrument error. The readings showed plasma densities fluctuating by factors of 20 to 30 within relatively short distances, something that shouldn't be possible in the outer heliosheath." After verification confirmed the readings were accurate, the team redirected New Horizons to focus on these anomalies. Thanks to its new autonomous capabilities, the spacecraft could now adjust its observations in real time based on what it was detecting, rather than waiting 16 hours for commands from Earth. The discoveries quickly snowballed. By April 2025, New Horizons had detected what scientists now call the heliospheric ripple, a massive wave-like structure at the boundary region that shouldn't exist according to any current model. By July, it had found evidence of what appeared to be a tunnel of lower-density interstellar medium penetrating deep into our heliosphere. But the most dramatic discovery came in January 2026, exactly 20 years after launch, when New Horizons began detecting patterns in cosmic ray intensities that suggested something extraordinary. The boundary of our solar system might not be a simple transition but a complex, structured region with properties unlike anything we've observed before. As Dr. Chen puts it, a spacecraft that was supposed to be dying is instead making the most important discoveries of its entire mission. It's like an athlete breaking world records in their final race. The question now was, how was this possible? How had the New Horizons team managed to squeeze so much science out of so little power? And what were the engineering innovations that made this second life possible? The answer lies in a series of revolutionary engineering approaches that have transformed how we operate spacecraft in deep space. Let's start with the power management system. Traditional spacecraft operations involve keeping most systems running continuously, which consumes substantial energy. New Horizons' adaptive hibernation system completely reimagined this approach. Dr. Rodriguez explains, "We developed what we call power microcycling, a technique where systems are powered up for milliseconds at a time, take measurements, and then shut down again. It's like blinking your eyes very rapidly instead of keeping them open continuously." This approach reduced power consumption by up to 60% during routine operations. But it required completely rewriting the spacecraft's operating system, a risky procedure when the spacecraft is billions of kilometers away. The software update took 3 months to transmit, notes Dr. Chen. And we had to include multiple redundancies and fail-safes. If something went wrong, we couldn't just drive out and fix it. The team also implemented what they call thermal harvesting, using the natural temperature gradients on the spacecraft to generate tiny amounts of additional power. By carefully positioning components and redesigning thermal pathways, they were able to recover about 3 watts of power that would otherwise have been lost as heat. 3 watts might not sound like much, says Dr. Jameson, but when your total budget is 190 watts, it's significant. It's enough to power an additional scientific instrument. Perhaps the most revolutionary change was in how the spacecraft makes decisions. New Horizons now operates on what engineers call a sliding autonomy system. The spacecraft continuously evaluates its situation, available power, scientific opportunities, and communication windows, and adjusts its behavior accordingly. It's like giving the spacecraft a set of scientific priorities and letting it decide how best to achieve them, says Dr. Rodriguez. We're no longer micromanaging its every move, but setting goals and constraints. This approach has allowed New Horizons to make discoveries that would have been impossible under traditional control methods. When the spacecraft detects an interesting phenomenon, it can immediately redirect its instruments to study it in detail, rather than waiting 16 hours for instructions from Earth. The communication challenge required equally innovative solutions. The team developed a new data compression algorithm specifically optimized for the types of scientific data New Horizons collects. Traditional compression algorithms are designed for things like images and text, explains Dr. Jameson. We created one specifically for particle counts, spectrographic readings, and the other specialized data types New Horizons generates. This increased effective bandwidth by 340%, allowing much more scientific information to be transmitted in the same amount of time. But perhaps the most ingenious solution was what the team calls intelligent data triage. The spacecraft now analyzes its own data on board and prioritizes the most scientifically valuable portions for transmission, explains Dr. Patel. Instead of sending everything back to Earth and letting us sort through it, New Horizons makes the initial judgment about what's most important. This approach has been remarkably successful. In one case, the spacecraft detected an unusual particle event that lasted just 17 minutes. Under the old system, this event might have been missed entirely or the data might have taken months to transmit. With intelligent data triage, New Horizons recognized the significance of the event, prioritized that data, and transmitted it within days. What makes these engineering innovations so significant is that they don't just extend the life of New Horizons, they potentially transform how we design and operate all future deep space missions. The techniques developed for this dying spacecraft are now being incorporated into plans for missions to the outer planets, interstellar probes, and even robotic explorers for other star systems. As Dr. Jameson puts it, we're not just squeezing the last drops of science from New Horizons, we're pioneering a whole new approach to spacecraft operations that will influence missions for decades to come. Just when you thought you understood how New Horizons was defying the odds, the story takes another dramatic turn. In August 2026, the spacecraft experienced an unexpected power fluctuation that initially baffled engineers. We saw the available power suddenly increase by about 7 watts, explains Dr. Rodriguez. That shouldn't be possible with a steadily decaying RTG. After ruling out instrument errors, the team made an astonishing discovery. The power increase coincided precisely with New Horizons' entry into one of the Cassel regions of the heliosphere boundary. Something about this region was affecting the spacecraft's power system. Dr. Chen explains the leading theory. We believe the RTG's thermoelectric conversion efficiency is being enhanced by the unique particle environment in this region. It's as if the spacecraft has found a sweet spot, where the physics of energy conversion works slightly differently. This unexpected phenomenon has led to a new hypothesis, that the boundary of our solar system might affect not just particle behavior but fundamental physical processes like energy conversion and heat transfer. If confirmed, this would have profound implications for how we design spacecraft for interstellar travel. Adding to the mystery, in September 2026, the team noticed that New Horizons' computer systems were operating more efficiently than they should be. The main processor was completing calculations faster while using less power, something that shouldn't be possible without hardware changes. Dr. Sarah Jameson notes, it's as if the computer is getting an efficiency boost from something in the environment. We're seeing processing speeds about 4% higher than our models predict, with no increase in power consumption. Some researchers have suggested that the extreme cold of deep space might be creating superconducting-like conditions in some of the spacecraft's circuits. Others propose that the unique radiation environment at the heliosphere boundary might be affecting semiconductor performance in unexpected ways. Dr. Hiroshi Tanaka at the National Astronomical Observatory of Japan offers a more radical theory. What if the laws of physics themselves operate slightly differently at the boundary between star systems? We know that quantum effects can be influenced by gravitational fields. Perhaps the transition from our Sun's influence to interstellar space creates conditions where certain physical constants shift very slightly. This theory, while highly speculative, would explain not just the power and computing anomalies but also some of the unusual scientific readings New Horizons has been detecting. It suggests that the boundary of our solar system might be a region where the fundamental rules of physics undergo subtle transitions.